Now we're going to do some qualitative analysis of phase portraits. We are working with systems of two differential equations with constant coefficients, so linear systems. Now notice that the origin is always going to be a critical point, but however we are going to assume that the determinant of the matrix A is not 0, meaning that the origin is the only critical point. Okay, only. There is no other solution than 0, 0. Then my point is to demonstrate how stability of the equilibrium solution at the origin and the general layout, how the phase portrait looks like, how it is determined by the eigenvalues and eigenvectors of the matrix A. So here is the familiar example, but now let me explain how to sketch the phase portrait if I don't see if I don't do it on a computer. So if I want to do to sketch it, so x1, x2. First I plot the axis. So then notice that these 1, 2 and 1, negative 2 are eigenvectors. So I'm going to plot the lines corresponding to these eigenvectors. So the line that passes through the point 1, 2 and the origin, and the line that passes through the point 1, minus 2 and the origin. So 1, 2 is like this. So this is 1, 2, and 1, minus 2 is like this. So this is 1, negative 2. Right. So another thing that we need to notice is that here the eigenvalue is 3 and is positive. Right. So here we have the positive eigenvalue along this line, and the positive means that as t goes to infinity, e to the 3t goes to infinity as well. Right. So which means that all solutions, they point away from the origin. So along this line, all the arrows, they point away from the origin, while the other eigenvalue is negative 1, so is negative, and if it is negative, it means that all solutions along this line, they point towards the origin. Well, but then clearly there is just one way to sort of fill it in, like this. So these are trajectories with some trajectories with the direction of the trajectories. That's a very schematic sketch. Of course, the real thing is on the left. So notice that the real thing is closer to the line 1, negative 2 rather than to the line 1, 2. But let's just ignore this. So the important point here is that all solutions, they designed like this. So they approach the origin first, and then they turn away from the origin. So when they approach the origin, they do so along the parallel to the line corresponding to the eigenvector with the negative eigenvalue, and when they turn and then go away to the origin, they do so sort of parallel to the other eigenvector 1, 2. And in this case, we say that the origin is a saddle point. Right, and then notice that the origin is unstable in the sense that almost every trajectory, well, except for these two trajectories that go exactly towards the origin along the line 1, minus 2, so they eventually turn away and go away from the origin. So that's why it is unstable. Right. So now it is this phase portrait is called a saddle point. So here is the other example. Again, let us sketch the phase portrait. So there are two eigenvectors, 1, 0 and 1, 1. So let's do 1, 0 first. This is 1, 0. I mean the corresponding eigenline, and 1, 1 goes like this. Notice that both eigenvalues are negative, so which means that all arrows, they point towards the origin. Well, but then it is a bit tricky. So there are two eigenvalues, negative So if R1 is negative 0.5 and R2 is negative 1.5, then notice that the absolute value of R1 is less than the absolute value of R2. So that's R1 here and that's R2 here. So it means that near the origin, the behavior of our system is determined by the eigenvector corresponding to the smaller eigenvalue. So that is R1. Far from the origin, it is determined by the eigenvector corresponding to the larger eigenvalue. So which means that if we are going to fill it in, basically there are two ways to do it. So if we could do it like this. So imagine that we could draw trajectories that go like this. But this is incorrect. This is incorrect because here, if we do it like this, then near the origin, they become parallel to the eigen direction corresponding to the larger eigenvalue. So this is wrong. So instead, it should be like this. So far from the origin, they are parallel to the vector 1, 1, and near the origin they are parallel to the vector 1, 0. And here is the real picture, and you see it's pretty consistent to our sketch. Okay. Now here is the third example. That's something new. We haven't seen it before. Still, let's plot it. So that's the axis. Now again, there are two eigenvectors, two eigenvalues. So the first of them is 2, 1. So 2, 1 is something like this. That's 2, 1. And the second is is 1, 1. The 1, 1 is like this. Now, which one is bigger? So the eigenvalue that sits on the vector 2, 1 is 3, and on 1, 1 is 2. So 3 is bigger. So the bigger one determines behavior far from the origin. The smaller one determines the behavior near the origin. So which means that we are ready to kind of sketch the phase portrait. So first of all, both are positive, so which means that all directions are away from the origin. Then far from the origin, it's parallel to the vector 2, 1, and near the origin is parallel to the vector 1, 1. So far from the origin, parallel to the vector 3, 1 here, and near the origin is parallel to the vector 1, 1. Same thing here. So near the origin 1, 1, far from the origin 2, 1. Same thing here. So notice that the alternative would be something like, let me try to plot the alternative. So the alternative would be something like this, but this is not correct. And as you see, our sketch is quite consistent with the real picture. And in this case, when we have two eigendirections corresponding to positive eigenvalues, then we say that the critical point at the origin is a nodal source or asymptotically unstable node.